Welcome listeners. Again we have gathered here to discuss on the next half of our discussion on sedimentary rocks in the series of lectures on fundamentals of geology. So, after looking into the formation of sedimentary rocks and also different processes that are involved in the formation of a sedimentary rock, be it a clastic sedimentary rock or a non-clastic sedimentary rock, we will now plunge into the texture of a sedimentary rock, similar to that of when we discussed about igneous rock. First we discussed about how igneous rock is formed, and later on we also discussed uh, uh, on the textures exhibited by a series of igneous rocks. So, talking about texture in sedimentary rocks, broadly again it is divided into clastic texture and non-clastic texture depending on its mode of origin, that how it is getting originated. And like we have discussed, in case of your clastic sedimentary rocks, mainly your physical processes are involved, starting with the means erosion of a material getting transported to a certain place, then getting deposited there, followed by the process of diagenesis and lithification, which also involves the process of cementation. And we have also discussed about various cements that are involved in the process of lithification. And apart from that, we have also discussed that how non-clastic sedimentary rocks like limestone are being developed in nature. And broadly speaking, again there are three ways of developing your non-clastic rocks, starting with the chemical one, followed by the biochemical one, and also there is a class of sedimentary rock that are termed or as referred to as evaporites. So, we will also look into that aspect a little bit in more detail when we will talk about the classification schemes that are used to classify different sedimentary rocks. But first, to talk about your textures that are involved or that are exhibited by different sedimentary rocks. So, definitely like any other texture, be it in your igneous rock or in your metamorphic rock or even sedimentary rock, sedimentary textures refer to the shape, size and the three-dimensional arrangement of the grains, also the interrelationship between the grains that are the constituent particles or constituent minerals that are present in a particular rock. So, definitely in case of sedimentary rocks, when you are talking about sedimentary texture, generally sedimentary textures are primary, but there could be secondary textures as well. That might get formed when we will be talking about your non-clastic sedimentary rocks or chemically precipitated sedimentary rocks. So, the first consideration that should be taken into account is the grain size. Obviously, the grain size is an important factor in case of sedimentary rocks. Be it any rock, if I say be it in igneous rock, in metamorphic as well as in sedimentary, but in case of sedimentary rock, it also give you an idea about its origin. So, that is why the grain size is extremely important in case of sedimentary rock. For example, a rock having a coarse grain size have a different mode of occurrence with respect to a rock that is very fine grained in nature in case of sedimentary rock. And there are several statistical methods to separate these different classes of rock. So, we will be also talking about that. And regarding the size, first obviously we will be first concerned about the particle size. So, there are two well established scales. The first one is the Arden-Wentworth scale. That is widely used as classification system for sedimentary grain sizes, and it categorizes sedimentary grains based on their diameter, and obviously respective terms are assigned to it. So, it's you can say the Arden-Wentworth scale is based on the diameter of a particular grain that is constituting a sedimentary rock. On the other hand, there is another scale that is also very well established and accepted worldwide, that is the phi scale, which is a logarithmic grain scale. So, it is a numerical scale used to express sedimentary grain size in standardized as well as in logarithmic manner. So, the method of calculating your phi value, which represents or which will finally be used as a means you can say as an element within your phi scale. The phi value is calculated based on the sedimentary grain size, specifically the diameter of the individual particle. So, the phi value is equal to the minus of logarithm base 2 and your diameter. So, d is the diameter of the sediment grain, that has to be in millimeters. So, that is the scale, and for reference you can always say that a sediment grain with a diameter of 1 millimeter corresponds to a phi value of 0. So, you can also from this you can say that if your coarser if your rock is having coarser sediment grains or coarser particles in it, then it will have a negative phi value. If a rock is very fine, some grains are even less than your 1 millimeter diameter, which is the reference or the standard, then the phi value will be positive, because here we are taking a negative of the logarithm base 2 of your log diameter value. So, particle size based on this you can segregate into your based on the Arden-Wentworth scale as well as based on your phi scale. So, if you look at this simple table, you can say that the millimeter, this is your reference, that is your 1 millimeter, which separates very coarse sand from the coarse sand. So, that is your reference or that is your standard value, above which you have obviously positive values in terms of millimeters as we go from the size of sand to up to your granule, pebble, cobble and boulder. Obviously, the size of the particle is increasing. In that case, your phi value will be negative in nature. But when we are reducing the size of a particular particle or a sediment, then again if I am taking a very fine particle that is present in a sedimentary rock, and if I want to scale that, then again you will apply the same phi calculation, and you can say that when you are reducing the grain size, your phi value is going into the positive end. Like for example, so this is again the standard, that is 1, which separates your very coarse sand from the coarse sand, and as you go beyond it, as you are reducing it further, or the size of the particle is much lesser than that of 1 millimeter, in that case it grades into sand to silt finally into mud. And based on this, obviously based on this particle size also, your rocks or the sedimentary rocks are classified into these broad groups, starting with the conglomerate or the breccia, a type of sedimentary rock. You can see you have this large clasts like this, or the large fragments of rock which are generally rounded in nature. In that case, they will be considered under conglomerate. In this case, when the fragments are mostly your angular in nature, they will be considered under the group of breccia. Then you also have based on again the scale or the particle size, you have sandstone, you have quartz arenite, feldspathic arenite. We will be also looking into that how your sandstones are getting classified into various classes. You have this quartz arenite, feldspathic arenite and your wake as well. And then finally, again if you reduce the particle size further, then you will get siltstone like this, and the result of siltstone, you can say the formation of shales like this one you are looking at. Then finally, you have the finest one, that is clay, or simply you can think of mud. So, the resultant sedimentary rock which is dominantly constituted by your size particles will be your mudstone, or also some people say as clay stone. Apart from that, like I was mentioning about some statistical references that are used to determine or to segregate the different textures in a sedimentary rock. So, one term that comes into place, that is sorting, and it refers to the degree of similarity in particle size within a sedimentary rock. That means, if there is an uniform grain size throughout a sedimentary rock, where your all the particles that are present in a particular sedimentary rock, they are of more or less same grain size or very similar grain size, in that case I will say that it is very well sorted. But on the other hand, the other end member is that there are large fragments that are present, as well as there are very fine particles that are present, be it in the ground mass or in the matrix material, they are also present. In that case, you can see there is a large difference in the particle size with respect to the large angular fragment or rounded fragment and the ground mass that on which the angular or rounded fragments are simply stuck or kind of floating. So, in that case, we will simply consider it as very poorly sorted. So, it also reflects it's again I was referring to it that again and again texture, the understanding of texture is extremely important, because it will give you an idea about the kind of environment, about the kind of transportation through which a sedimentary rock has formed. So, you can say that well sorted rocks have grains that are all about the same size, like I was mentioning, while poorly sorted rocks contain a wide range of your grain sizes. Then your well sorted rocks typically indicate uniform sedimentary processes. Obviously, if some process is going on at an uniform rate, then the material that are getting transported with it will be of similar size or of similar weight as well, because then obviously they will be segregated in an uniform manner, like that we get to see in your beach environment. Again, the poorly sorted rocks suggest a mixture of your large grain size and very fine or intermediate grain sizes as well, and they reflect high energy depositional environments, like that we get to see in case of alluvion fans. Also, you can take a simple example like that of landslide, that when a landslide is taking place, there will be always a mixture of material containing large boulders, small pebbles, sand, some mud, some clay minerals or some clay particles are also being transported in a high energy manner, and they are getting dumped at certain place during an event of a landslide. So, you can say that a landslide typically represents a process of your very poorly sorted sedimentary rock, or the sorting in the fan deposit, for example, that has been formed as a result of a landslide will have very poor sorting in its within the particles that are present in the sedimentary rock. Then you have another statistical reference, that is skewness or skewedness. So, it measures the asymmetry of the particle size distribution within a sedimentary rock. So, if I am saying that a specific rock is giving you a very symmetrically skewed or very symmetrically skewed distribution of the particle size, then I will say that all the means there is a, in terms of frequency, there is a uniform distribution of your larger particles as well as your smaller particles. But if I say that your skewness is positively skewed or it is negatively skewed, like this graphs, you can see this is the coarser end of the graph, this is your frequency, and this is the fine end of your graph. Similarly, in this one, again this is the coarser end, so you have a coarser particle tail kind of here. In this one, positively skewed one, you have a fine particle tail here. So, you can say that a positively skewed distribution indicates that there are more fine grained particles compared to the coarse grained particles. Similarly, a negative skewed distribution suggests that there are more coarse grained particle in comparison to your fine grained particles. Then obviously, again like I was mentioning again and again, that skewness also can provide information about the dominant transport processes and sorting mechanism. So, you can see again that the skewness, which also reflects the texture of the particles that are present in the sedimentary rock, will reflect or will provide you some information about how it is being transported through its process of formation. If I take an example, a positively skewed distribution may indicate winnowing or selective transport of fine grained materials, whereas a negatively skewed distribution like this one could result from rapid deposition or abrasion of coarse grains. Then you have another statistical consideration, that is kurtosis. So, kurtosis measures the pickedness or flatness of the particle size distribution curve. So, a leptocratic curve like this indicate a sharp peak and relatively narrow range of grain size. That means the grains or the particles that are present in that rock are of mostly similar grain size. That is why it will have a specific peak in it. On the other hand, a platykurtic distribution with low kurtosis has a flatter peak and a wider grain distribution. That means, in case of a platykurtic curve, you can simply say that obviously there is a wide distribution in the grain size. So, you will have coarse grain and particles in it. Also, you will have intermediate as well as fine grain particles in it. And based on that, based on this formula of kurtosis, you can also calculate that whether you are having a positive value of the kurtosis which reflects leptocurtic graph, or whether you have a zero value of the kurtosis which reflects a mesocratic graph, and whether you have a negative value of your kurtosis which reflects your platykurtic graph. Then also the other consideration is obviously the form or the roundness of a particular grain or a particle. So if I simply say that a grain is getting transported to long distance from one place to another place, then obviously during its transport it is highly possible that apart from your different agents of chemical weathering like oxidation and carbonation, apart from that you also have physical weathering during its transport, because you are not transporting a single particle, you are transporting a load of particles. So, your particles also will get abrated due to physical weathering between them, as well as during, because for example, again I will take this example that some particles are getting transported in a river, for example. So, your water is taking that load and it's transporting different particles of different size, for example, to one place to another place. So, if this transport distance is very high, then what will happen? Then finally, whatever particle will reach to a certain place or get deposited to a certain place will be of obviously finer size, because by that time it has been physically abrated due to the effect of physical weathering as well as due to the effect of chemical weathering. Finally, the particles are being reduced to a specific size. So, and also during this journey, the individual particle will achieve certain roundness and sphericity rather than you can say a set of particle which has been transported to a very short distance. In that case, the physical aberration will be less. Obviously, the effects of chemical weathering will be less. So, your particle or the form of the particle will be much angular in nature and not like a rounded one which has transported from a larger distance to somewhere else. But if it is so, so you can say the roundness or sphericity of a particle is directly reflecting that how far a particle that is present in a sedimentary rock has been transported from how far a distance. So, if it is getting transported from a short distance, generally obviously you will get angular fragments in it, but in case if it is getting traveled a larger distance or it is getting transported larger distance, the resultant particles will achieve a near rounded or near sphere kind of shape. So, based on that, there are two formulas that can be used: formula for sphericity, where your V is the volume of the particle and A is the surface area of the particle. Similarly, you also have a formula for roundness. You can say that dH is the maximum ferrite diameter and dP is the minimum ferrite diameter measured perpendicular to dH. So, this simple graph also here reflects that if the distance of transport is long, it is likely that you will get more rounded or more spherical shape or form of a particle that is the constituent element of a sedimentary rock. Then you also have you can say the orientation of grains that will define the fabric. You also have the packing of the grains, how good your packing is, that will also define, and again the other component of texture, that the interrelationship between the grains, interrelationship between 2, 3, 4, even more grains which are having a shared grain boundary. Some grains are getting shared or the grains are sharing their boundaries. So, based on that also the grain contacts, you can also have an idea about the fabric of the sedimentary rocks. So, again if I look at the packing, there are various kind of packing like this. So, based on that you can say the maximum theoretically maximum packing can be achieved if you are having a cubic packing like this, and the minimum if I look at for the rhomboedral packing like this, then you will get a minimum packing within the grains. Then apart from that, and this packing is also very important because it also regulates or controls the idea of your porosity and permeability. So, your porosity and permeability, these are the new terms that are getting introduced here. So, porosity is nothing but the number or the volume of pore spaces that are present in a rock. Specifically here we are talking about sedimentary rock. So, I will say that a sedimentary rock having more porosity is or could become a very good reservoir for an oil, like we discussed in the first few slides in our first part of sedimentary rocks, that obviously sedimentary rocks, they provide reservoir system for your oil and natural gas. So, it depends nothing but on the packing of the grains that are constituting that particular rock. So, if your packing is high and also it reflects, so your packing obviously it strongly also controls the bulk density of the rock, and it also controls your permeability. Permeability means it is the number of connected pores that are present in a rock. It is not always necessary that a rock having high porosity has high permeability as well, or the other way, that a rock having high permeability also has a high porosity. But generally your highly porous rock generally also gives your high permeability, because if the number of pores are high, there is a means you can say there is a probability that the connection between in the pores is also high. Again, generally speaking, it is not a thumb rule that obviously porosity is same as that of permeability, is not a thumb rule. So, it is, and also like I was mentioning about the interrelationship between the grains. So, there are again these kind of contacts that you can see in a sedimentary rock. The point contact, when your grains are just touching the another grain at a point. Long contact, when they are kind of surfaced on one another. Then you can have concave or convex kind of contact. Also, you can have sutured contacts where your grains are kind of attached in a dented manner with respect to one another. So, one of the example of grain orientation, it is a very popular and very commonly occurring example, that is the pebble imbrication. So, you can see that these grains, large grains, they are aligned in a particular fashion under the action of the current. The current means it is just the transporting medium. It could be wind, it could be your water, like that you can see in this river. There are these large boulders, also some cobbles that are aligned in a particular fashion like this. Just like you can simply think of books in a library which are present in a manner like this, in a tilted fashion. There are books that are placed in a manner like this, so in an inclined way. So, you can simply think in a manner that this is the movement direction of the transporting medium, that is wind or water, and it is getting due to that these boulders or cobbles, they are arranged in a specific manner like this. So, based on this you can also find out, even if you are looking at a deposit where there is no transporting medium nearby, you can also make an idea that when that deposit or that sedimentary sequence was formed, you can have an idea what was the paleocurrent direction, means what was the current direction during the time of formation of that particular sedimentary sequence. So, based on this pebble imbrication, you can have an idea about the paleocurrent direction. So, again there are broadly two kinds of pebble imbrication. One is class supported, where there are larger or coarser grains that are present here, and again you have the matrix supported, where obviously there will be some classed, but the dominance of the fine grain matrix material will be more. And in this case of in case of a non-imbricated pebbles, you can't make out the paleocurrent or current direction. So again, coming into now after texture, there are again consideration about classification of your sedimentary rocks. And just to start with, there are again various schemes of classification. To start with, the mineralogical classification. So based on the mineralogical composition, we can classify sedimentary rocks broadly into two groups: your allogenic materials or minerals, or orthogenic minerals. So your allogenic minerals, these minerals are formed elsewhere and being transported to a specific area of deposition where your finally your sedimentary rock is being formed. In case of your orthogenic one, it is not getting transported from somewhere else, it is getting precipitated, be it for example chemically or biochemically, it is getting precipitated at a certain place. Based on this two n members allogenic minerals, where the minerals that have formed somewhere else are getting transported to a place where your rock is being formed, and you also have the orthogenic minerals which are simply getting originated at the place of the formation of sedimentary rock. So you can see there is a function of transportation, also a function of distance. So based on that, based on the mineralogical criteria, whether they are allogenic or orthogenic in nature, you can classify certain rocks like sandstone, feldspathic sandstone or arkose into one group. These are obviously allogenic, they will be constituted of your allogenic minerals. Then you have, for example, feldspathic sandstone or arkose. These are also dominantly, it means, constituted by your allogenic minerals. Then you have shale, argillite, mudstone. Again you have minerals like quartz, limonite, goethite in this kind of rocks. But in case of your chemically precipitated rocks or the non-clastic rocks, so these three, the first three are obviously clastic rocks. The fourth one here is your non-clastic rock, which is a result of your chemical precipitation. Here you will find these minerals like calcite and dolomite. So these are also the result of your mainly your chemical precipitation. Sometimes some biochemical precipitation is also involved. And also, if I look at the minerals in order of increasing stability in case of your sedimentary rocks, again if I think about the Barnes reaction series that I discussed when we discussed about igneous rocks, and we looked at the order of crystallization. Simply following that order, you can simply relate this thing with the igneous, those 9 you can 9 silicate minerals, your ferromagnesium silicate minerals and non-ferromagnesium silicate minerals. Based on that also, you can say that the unstable ones, your olivine, pyroxene, which were the first one to crystallize in the order of crystallization of the igneous rock, here in case of the sedimentary rock, these are really unstable in your mineral stability series. So your olivine, pyroxene, plagioclase and hornblende, these are the least stable minerals, and the most stable minerals are your muscovite, clay minerals, quartz, tourmaline, zircon. So again, quartz, muscovite, you can remember that they were crystallizing at the last stage or in the later stage, if I simply relate it with the order of crystallization of the igneous minerals or the silicate minerals in igneous rocks. So, and in between them you have sphene, epidote, kyanite, sillimanite, magnetite, garnet. So kyanite, sillimanite, these are mainly metamorphic minerals, means formed during the metamorphism of a rock. We will be discussing about metamorphism after we end our discussion on sedimentary rocks. So you have the first class of this classification, that is based on mineralogical composition. Then you also have classification based on chemical composition, based on the percentage of silica, siliceous deposit, carbonate deposit, ferruginous deposit and phosphatic deposits as well. Then based on texture, like I was mentioning, you have broadly you have two classes, clastic sedimentary rocks and non-clastic sedimentary rocks. So based on that, you can have these broad two groups based on again size and shape of grains, like we discussed in texture. Based on size and shape of the grains, you can segregate conglomerate breccia together, different kinds of sandstone together, and also sometimes shale and mudstone together. Again, these are or your clastic rocks. Then you have these three classes. The first one is your based on the size and shape of the grains. Rudaceous one, they are characterized by the presence of extremely large constituents in them, like that we get to see in conglomerate or in breccia. Then you have the arenaceous one, which are mostly dominated by the group of, you can say, your sandstone. So in that case, you will have a grain size between 2 millimeter and 1/16th of millimeter, and these are called arenites. They are generally they are well sorted in nature in terms of their maturity or sorting. So your source index is the ratio of feldspar to the rock fragment. Maturity index is the ratio of quartz to the feldspar and the rock fragments, and your fluidity index is the ratio of sand to your matrix. And then you have these different schemes of classification of sandstone based on the percentage of quartz, feldspar and the lithic fragments. Similarly, your this classification by dot that shows the presence of quartz arenite, subarcose, arkose, arkosic arenite. So these are the different classification schemes, and obviously it is a matter of detailed discussion, not at the fundamental level. Obviously, this classification, each and individual rock should be discussed in greater detail for other advanced level discussion on sedimentary rock. But just to summarize here, that here sandstone can be classified based on mainly the presence of your quartz, feldspar and lithic fragments, and based on that they are segregated as arenites, wackays and mudstones. And the other class that is based on the size of shape of grains, that is argillaceous, which are mainly again the representative rock type is shale. So here again means if I look at this, then the mainly constituent grain size will be below or finer than 1/16th, and again you have the clay minerals that are dominating and this particular group of argillaceous sedimentary rock. Then you also have a classification scheme based on depositional basin, the extrabasinal or allochthonous sediments. Also you have the other kind, that is intrabasinal or autochthonous sediments. So just by from the terminology, it reflects that the allochthonous sediments are formed from the weathering of pre-existing rock placed away from the basin, like we were discussing about when we discussed about the sorting of a particular sedimentary rock. So in this case, if they are getting transported to longer distance to a depositional basin, then obviously they are clastic, and mainly they are dominated by the group of sandstones. Also, if there are angular grains, or if it is poorly sorted in some cases, then they are mainly conglomerate in nature. But in case of your intrabasinal or autochthonous sediments, they are mostly chemical precipitates, and again they are same as that of the non-clastic rocks, like that of your minerals like calcite and dolomite will be formed or will be present in that particular rock. So you can also relate this with this extrabasinal or your allochthonous sediments. They will mainly give you dominantly clastic sedimentary rock. In case of intrabasinal or autochthonous sediments, they will mainly give you non-clastic sedimentary rocks. So here I'll come back to limestone when I'll be discussing about limestone in detail in the last part of your discussion on sedimentary rocks. So here I would like to stop on the second part of our discussion on sedimentary rocks. Thank you.